Professor Arutyunov, again from the Semenov Institute. And this presentation is about the relative conversion of light alkanes at their partial oxidation.
Ladies and gentlemen, thank you for invitation for this organizer. Thank you for invitation on this meeting. My presentation concerns the possibility of processing of hydrocarbon gases, both oil and natural gases, with high enough content of heavier hydrocarbons. Such picture is very usual for many gas and oil producing sites, especially in remote areas. And that is because due to estimations, more than 100 billion cubic meters of hydrocarbon gases annually flared or vented all around the world. And to my mind, these figures are significantly underestimated, because only for Russia, these more reliable figures are between 20 to 40 billion cubic meters annually. So it is a very big, when you fly over the West Siberia, you can see dozens and dozens of such flares in this area. And it is not only a waste of very variable hydrocarbons, but there are of course some ecological problems, not speaking about Kyoto Protocol and so on. And the problem, because the oil industry needs crude oil, crude liquids, and gas industry needs trade-grade natural gas, and there are such marginal products as ethane, propane, and butane, which is very difficult to transport from these remote areas. So significant part of the significant share of these gases are flared. Even old producing countries such as Europe, USA, practically all these gases are processing. In Russia, more than 50% of propane butane are burned, and you see that the share of ethane which extracted and used is only several percent, and even prospects for ethane recovery is not very promising. That is because Dr. Sinov facilitated my task, because he said why and how severe Russian gas and oil industry needs low-scale technologies, because you see that conventional GTL technologies needs very high capacity, and if you try to use the process with capacity less than 1 million ton per year, you will see that there's a very sharp increase in capital cost, in operating expenditures. All expenditures rise very sharply. So both oil and gas industries needs low-scale technologies to convert, first of all, such oil-associated gases and sometimes natural gas to more easily transportable liquids, first of all liquids. There are only few alternative processes, alternative to thin gas route, and among them one of the most developed and to my mind one of the most promising is direct oxidation of hydrocarbons into methanol and other oxygenates. During several years we are involved in investigations, both theoretical and experimental. Here our experimental laboratory device, and we even have some experience to operate with a pilot plant with such capacity, about 100 tons per year. And as far as it concerns methane, dry natural gas, methane conversion into methanol, we believe that we understand the chemistry of the process well enough. It is not a very simple process, it's chain-branched, degenerated chain-branch process, and to describe the chemistry, you need to use several hundred elementary chemical steps, but nevertheless we believe that we understand this process, its peculiarities well enough. So on the basis of this understanding, we have developed the process, technological process. There are, of course, some disadvantages of direct conversion, the low, relatively low selectivity, low conversion by path, but there is also some significant advantages. First of all, it is very high simplicity of equipment, very simple equipment, relatively simple, of course. Because it, autothermal reaction, it doesn't need heat, external heat, it's oxidation process. It's a poor gas phase reaction, it needs no catalyst at all, it's gas flow reactor, so it needs no catalyst. So it is very useful for using just on methane or oil gas sites, producing sites. Besides, there is another waste room for such process, because Russian oil industry needs several hundred thousand tons of methanol, rough methanol, to prevent hydrate formation. This industry needs itself. So such low-scale processes are very interesting for Russian oil and gas industry. The process, of course, needs the process needs, due to low conversion per pass, the process needs recirculation of gas. It's intensive heat recovery, because it's high heat production, and outgoing gases may be used for power production, both for the process itself and for export. You see that although the chemistry is complex enough, the process may be shown by this simple their productions may be shown by this simple equation. You have that about half of the initial carbon, goes to liquid products, methanol and formaldehyde, and another half goes to carbon oxides. First of all, carbon monoxide, and to less extent to carbon dioxide. So on the basis of our investigation, such pilot plant with, industrial plant, industrial unit. So we think that it's not plant, it is unit with productivity 5,000 tons per year. It's just capacity which is most needed for gas and oil industry was projected, and there is agreement that in the next year, we believe that in the next year, the first such unit will be constructed on one of the Russian gas fields. So that is but this project was for methane, natural gas with higher hydrocarbons content, no higher than 10%. And if we will discuss the possibility of direct oxidation of higher hydrocarbons, we see that from one side the oxidation of higher hydrocarbons, of course, is much easier than oxidation of methane itself. But there is very few data, experimental, theoretical data on oxidation of such gases. But you see that the heavier hydrocarbon, the less pressure we need, the lower pressure we need. It's very significant from economical point of view. The lower operating temperature, it facilitates the survival of oxygenates, not very stable oxygenates. And what is the more important, the ratio of hydrocarbon to oxygen may be higher. And that is the same that if we will have higher extent of conversion. For methane, as assured, we may have selectivity, to have selectivity about 50%, we may have a rate of conversion no higher than 4 or 5%, and for other hydrocarbons it may be significantly higher. But so if we will oxidize the mixture of such gases, it's natural to expect that first of all higher hydrocarbons will react and methane will be left in the mixture. But the reality is not so simple, because methane and ethane is the most untypical hydrocarbons in methane family. They have no CH2 groups, and methane have no CC bonds at all. And when we deal with these two gases, we use that ethane is one of the main products of methane oxidation, and methane is one of the main products of ethane oxidation. So these two gases formed such subsystems, and then there is impossible to deal with oxidation of one of this carbon without taking into account the other. So we made some experiments and calculations, theoretical kinetic calculations concerning the oxidation, mutual oxidation of methane-ethane mixtures. We derived such a value, which is the ratio of these hydrocarbons, ratio of these hydrocarbons in the final stage and initial stage of the reaction. You see that although this ratio rises with oxygen content, it is very close to 1. So it's practically 1 at low oxygen, and even it rises sharply at high oxygen, it is less than 2. So these two hydrocarbons oxidize symbotically, practically symbotically. This solid points is experimental, and empty points is kinetic calculations, or calculations. And also about if we change the percentage of ethane in mixture from the oil range from 1% to 80%, you see that this ratio alpha is also very close to unity. So both these hydrocarbons oxidize together, and it is practically impossible to selectively burn out, for example, ethane from the mixture without burning the methane. It's these two hydrocarbons in oxidation are very closely tied by mutual reactions. But as far as this concerns the heavier hydrocarbons, butane and propane, you see that in this case the picture is very different. If you have high enough oxygen in the mixture, you may practically completely burn out butane and propane, and this figure, this value beta, is relative change in percentage of each hydrocarbon. And the percentage change of methane is negative, which means that percentage in mixture rises, and not only to conversion of butane and propane, to burn out of propane and butane, but also due to part of butane and propane converts into methane as a product. But if we have low oxygen in the mixture, you see that the conversion of this higher hydrocarbons drops sharply, and methane convertage became significant. That is because although these hydrocarbons react, have weak, more weak bonds and